Welcome everyone, and I'm going to be talking about some of the concepts in reinforcement learning and try to give you some of the intuition as to why they're necessary and how they help us solve different types of reinforcement learning tasks. So with that in mind, here's an overview, an outline of some of the topics we're going to cover. First of all, the goal of reinforcement learning, we'll get into that. And this is actually the second part right here, greedy versus Epsilon-Greedy. This is actually a key idea, concept in reinforcement learning because in general, greedy algorithms don't work in reinforcement learning. And that has to do with the reward system, which involves moving from one state to another state, taking an action. And the rewards can be positive, zero, or negative. And that's really the thing that prevents greedy learning, greedy algorithms from working. So what we end up doing, in essence, a little bit of foreshadowing here, is using a greedy algorithm 90% of the time, generally, and then 10% of the time is going to be random. And so I'm going to just jump right into this thing. This is what we're going to be looking at. And as you can see, we have a set of states. This is a very simple task called the n-chain task. And the idea is that we want to go from the leftmost to the rightmost. Simple enough. And we have rewards and actions. And there's only two actions, each of which has a reward. So if we look at action 0, the reward is 0. And we see action 1, the reward is 3. However, in order for us to go from left to right, we have to take the action whose reward is 0, because the action whose reward is 3 takes us back to the beginning state. Therein lies the issue with using a greedy algorithm. And during the course of the session, we'll see how to handle this. Another topic is exploit versus explore, and it's exploit in the neutral sense of the word. I prefer to use the word leverage, but the industry and reinforcement learning uses exploit versus explore. And this is really about the exploit would correspond to taking a random action, and exploit is for the greedy algorithm, and explore is for taking a random action. Another important aspect is this discount factor, and I'll show an example involving finance where that comes into play. And so we end up not just adding rewards, we have to discount them as we go along, and that's where the discount factor comes in. N-chain task is what I just showed you, a little bit of pseudo code, and then I'll get into some Monte Carlo versus TD learning and the differences between them and when you would use one versus the other. Another aspect of reinforcement learning is deterministic versus stochastic. And then we're going to go from DFA, deterministic finite automata, to a Markov decision process, which is the way to model reinforcement learning tasks. So then after that, we're going to do a little extra stuff. I'm going to go fly through that. We probably won't have much time left, but just some of the concepts that you can then study and learn about after you've gone through this session. A little bit, some of the reinforcement learning libraries, some of the people, and then some links that'll be helpful for some additional material. So with all that in mind, the goal of reinforcement learning is to maximize the expected future return. And as you saw from those states, we end up, if we can get from the leftmost to the rightmost, we end up, when we're going to calculate the return, we're going to take each reward and we're going to multiply by a discount factor, but it becomes, you end up with powers of the discount factor. So instead of just discounting by gamma times a reward R, the next state would become gamma squared times that reward and gamma cubed times that reward. Now, if gamma is between 0 and 1, that's going to end up being a finite amount, and I'll show you why that is the case. So just going back to something I already mentioned, the rewards can be positive, 0, negative, and they could all be negative. In fact, in some scenarios, in some reinforcement learning tasks, they are negative, such as trying to get from the start of the maze to the exit. That's one strategy that can be done. And of course, I'm sure you've heard of reinforcement learning solving tasks such as playing chess games, playing Go, teaching robots how to walk and run and this and that, all that sort of stuff. And so just to give you an example of negative rewards. If any of you have adult children attending college and you're paying for their education and a 4-year degree, well, at the end of each year, it's a negative reward. It's money paid out for the, the classes and so on and so forth. But at the end, you have the payoff, which is everything's going to be real nice. You'll be able to get compensated, reimbursed for the costs of college and so on and so forth. Everything works out fine. Another example would be the lottery. People spend a lot of money in some cases and can, of course, get a huge payoff. I don't play the lottery. I also don't gamble. So, but from what I understand, once again, people can spend a lot of money and they can get a large payoff, although that probably doesn't happen nearly as often as people would like. So now, exploit versus explore. Now, it might seem like a contrived artificial sort of a concept, but there's actually a real life counterpart to this, whereby the one that I like to use is, suppose you're moving to a new city. So you're leaving the current city, and you're driving, and someone says, let's go to our favorite restaurant one more time. That's an example of leveraging your knowledge or exploiting. You may have several of them, that's fine. You pick one of them and go to that restaurant. Then what happens when you go to the new city? You don't know anything. I mean, you can look at online reviews and so forth and make a decision based on that. But you end up probably at the beginning for a while, you start going to one new place after another because you are exploring. Now, the interesting thing is that after a while, maybe 10, 15, or 20 restaurants, what tends to happen is that people go, well, I don't feel like going to a new place. Why don't we go to that 7th place that we went to, or the 9th, or whatever your favorite was? So you're starting to shift from a fully exploring mode to more of leveraging what you know. And eventually, for most people, they end up 80, 90% of the time going to restaurants that they like and occasionally going to a new restaurant. So that's how it can shift from a fully exploratory mode to this mostly exploitation type of mode. And this is relevant for reinforcement learning tasks. And so a couple of other examples that I thought of was learning how to ride a bicycle, which I, lo these many years, I still remember that experience, and training a robot to walk or to run. And both of these involve one particular type of algorithm that's favored. It's called TD learning, which we'll get into, and you'll see the rationale for using that algorithm. So greedy algorithms try to select or indicate or require that you select a maximum available reward at every step. And as you saw very briefly in that example, that takes you back to the original state, the initial state, so you can never escape. Now, examples of greedy algorithms spanning trees, linear programming. Integer linear programming, interestingly enough, if you change the condition from just maximizing an objective function, and you want the maximum integer value for the objective function, that becomes an NP-hard problem. So you don't know, you could be arbitrarily far or arbitrarily close to the actual solution. So there's a big difference when you introduce the word integer with various types of programming tasks. And so, as I mentioned before, Epsilon-Greedy, to combine, generally it's 90% and 10%. So the discount factor, which is necessary whenever we're going to calculate rewards of future tasks, because the idea is that every time you change state, it's like a time step. And so if you have, for example, $100 today versus $100, say 5 years ago, or $100 in the future, from today's terms, which one is worth the most? It's not the one in the future. In fact, what accountants do is they calculate something called NPV, net present value. So they have to discount the future value, bring it back to the present. And so the future values are being, in today's terms, are of continue to reduce in value. And the same thing applies with rewards. And generally speaking, this value is usually, you'll see in articles, is the Greek letter gamma, so G, gamma, same idea. And so that value typically is between 0.9 and 0.99. It's a hyperparameter. And it can be very, in general, in reinforcement learning, when you have hyperparameters, they're very sensitive in the sense that a very minute change in a hyperparameter can produce vastly different results. It's kind of like, reminds me a little bit of fractals, where you get some very nice, beautiful pictures, and then you change one of the hyperparameters, and suddenly you get a drastically different image displayed. It's kind of just by analogy. That's kind of what it reminds me of. So then one more thing before we actually go into the diagram. And so just a little bit abstraction here. Suppose that we have a set of states, and so we can take them in any sequence whatsoever. And when you follow a set of states, that's called a trajectory. And when you get to the final state, there can be more than one. When you reach a final state, that trajectory is called an episode. It's like a game. So game over when you reach a final state. So let's suppose that we take some arbitrary trajectory, and it goes through these states S1 through Sn. And we get to those states by taking corresponding actions A1 through AN. And we get the corresponding rewards R1 through Rn. So how do we calculate the future return? It's going to be, as you can see in the screen, R is going to be equal to the first reward plus now the discounted value of the second plus the gamma squared times the third, and so on and so forth, all the way down to gamma to the n minus 1 times reward Rn, which is the reward at the nth state. And so you could say, well, could this be infinite? Not if gamma is between 0 and 1, for the following reason. Suppose we set R max equal to the maximum of these rewards. There's going to be one because it's a finite list. And so we then replace each of the R1 through Rn with R max. Well, that means that R is going to be less than or equal to this expression here, because the R's are replaced with values that are possibly bigger. And so we factor from here, we factor out R max. We get a partial geometric series whose sum equals this expression. And as n goes to infinity, arbitrarily large, since g is between 0 and 1, the numerator becomes just 1. So this expression here is less than or equal to R max over 1 minus g. That's the upper bound. Now, of course, this is when you have a positive return. What if they're all negative? You can still do something similar, and you calculate a lower bound for the future expected future return. So it's always going to be bounded between a negative number and a positive number. Okay, so now we're ready. As you saw before, we have 5 states. We want to go from the leftmost to the rightmost. And as you can see, action 0 is what we want to take for all states. However, the reward is 0 in all cases. The reward 30 here is the big payoff. Whereas the action 1 has reward 3 in all cases, just to make it simple. So that means that if we follow the greedy algorithm, we can never escape this state. And if we happen to ever be in this one, again, it brings us back here. Now, here's another possibility. What if we just stay in this state and just spin around indefinitely? We have a reward of 3 after 10 times. Wouldn't we get this? Not quite, because as we saw, the maximum possible return is going to be R max over 1 minus gamma. Now, all of the rewards are 3, so it's going to become the fraction. This fraction here is going to be 3 over 1 minus g. So if, well, back here, if g is equal to 0.9, we get 3 over 0.1, we get 30. So if we set the discount factor to a value that's less than that, then however many times we spin around here, it'll always be less than that. So that's not an escape route to get a reward future return exceeding this value over here. So what do? Well, we can simulate this, exploit and explore this Epsilon-Greedy algorithm in the following way. Let's suppose we have a coin that we toss. And if the coin turns up heads, we take action 0, and otherwise we take action 1. So obviously what we need is to heads followed by another and a second and a third. So we need 4 consecutive heads, each of which has probability 1/2. So it's 1/16. And we know that eventually we will have a sequence of 4 consecutive heads thrown. Another example would be, let's say we toss a die. And if we get a 1, then we'll take action 0. Otherwise, we'll take action 1. So there's 1 chance in 6 that we'll have heads, a 1, and 5 out of 6 if we get some other value. So once again, we can traverse this from the start leftmost state to the rightmost state, then it's going to be 1/6 each time, so it's going to be 1/6 to the 4th power, whatever that turns out to be. So that's the essence of the Epsilon-Greedy algorithm. Now, this example here, I just want to show you, is how we can actually simulate the example of leaving a city and that we know we go to a new city, we're doing fully exploring all the time, and then over time it decreases. This is how we could do something like that. We start off with a value epsilon, this is epsilon, epsilon min, epsilon delta. We start with a value of epsilon equal to 1. And in this while loop, we generate a random number r. If r is less than epsilon, we'll take a random action. Otherwise, we'll perform greedy. Now, these would be 2 Python functions, which obviously aren't here. And then what happens is we decrement epsilon by this amount. In this case, it's 0.01. Eventually, epsilon will become 0 or negative. We don't want to allow that. And we actually want to do is make sure it's never less than our minimum value, which is, in this case, 0.1. So after 90 iterations, epsilon will be at its minimum value, which is 0.1. And so what does that mean? Then every subsequent time, we're going to select the random action based on the value of r being less than epsilon, which will be approximately 10%. The other 90% will do the greedy action. So that can simulate that scenario as well. Now, you can write code where you have all sorts of conditions, different stages of a game. You might change the minimum value for epsilon. You might cause certain things to happen faster, make people respond more quickly, all sorts of things that you can do. So just to convince you, if you're not already, that epsilon-greedy is a generalization, if epsilon is 0, r will always be bigger than that. And so you'll always be doing the greedy algorithm. If epsilon is always 1, then r will always be less than epsilon, and so it'll always be random. So that means the greedy algorithm, it really is a special case of epsilon-greedy, or if you want to look at it the other way, epsilon-greedy is a generalization of the greedy algorithm. Okay, now got to shift gears a little bit. When we're going through, in this example, we have, it's very simple, we have 5 states, and we have 2 actions, 0 or 1. In general, you can have hundreds of thousands of states, millions of actions. And so as you go through these different trajectories, you could be looping around, coming back, going forward. There's no way to really predict where it's going to be because there's a certain randomness involved in selecting or following different trajectories and paths. So what you can do is keep track of the cumulative rewards when you take a state action pair. So in this example, we have, here I have n states, and then across the top, just 4 actions, just because that's all that fits on the screen. So in our example here, we would have 5 rows for the n-chain task, and we would just have 2 states. Simple enough. So we can initialize this with all zeros. And so let's arbitrarily, without loss of generality, let's say we're in state 0 and we take action 0. Now, that combination will take us to, I don't know, state 3, for example. It's not listed here, shown here, but when you take given a state, you take an action, you get some kind of reward, positive, 0, or negative. That value is then used to update this particular, whatever the value is here. In this case, it's initially 0. Now keep in mind that the selection of the action involves Epsilon-Greedy. So if we do a greedy choice, for example, if we do a random choice, it could be any of these. If we do a greedy choice for actions, well, which one has the maximum? They're all the same, they're all 0. So you can add the rule, well, if there's multiple values that are equal, take the leftmost value of those equal values. So that's why I chose this one right here. And so now, so you'll increment by whatever the reward is from taking the, from state S0 and taking action 0, which I said, let's say it's state 3. Now we repeat this process once again, and so we end up with something like this. Now, if you'll notice here, one thing, pretend that there's only one non-zero value, the leftmost value. So that would be 2.1, 5.5, 4.3, 2.2, 6.4. If we use the greedy algorithm exclusively, that means we'll always be picking the maximum value, the action that has the maximum value for that state action combination. That means we'll always be hitting those same values like over and over. We will never be exploring the other ones. And so the only way we can get to those other ones is through the Epsilon-Greedy algorithm, which makes sense that we need to explore a lot more states, not just the one state action pair for each of those rows. So I hope this kind of I know I'm going really fast through all this. I just want to make sure that I can cover everything, and I believe it's recorded, so you'll be able to have a chance to view this later on. So I'm not going to go into detail with this because there's a link in the final slide for an article that contains this formula, and it's a very well written article. It's on, I think it's on Medium. So I recommend reading that article, and a lot of that will make sense. The only thing that's new here is this extra new hyperparameter called alpha, which is the learning rate. It's kind of like the learning rate in deep learning. When you're doing backward error propagation, you've got the loss function, the learning rate, and the optimizer. It's sort of like that kind of idea. And so now, fasten your seatbelts because there's a lot of stuff in here, very high level. I'll just kind of take you from what we just did to generalize it to the most general scenario. The first one is really what we've done is we've looked at an example where there's a fixed number of states and there's a fixed number of actions. That can be typical of when you have a rectangular grid. There's one that's called grid world, which is a 3x4 task, 3x4 grid rather. And there's also, for example, a maze can be represented in a rectangular array. And so that's where the Q table comes in. Now, what happens if you have an increasing number of states, a dynamically increasing number of states, which can happen when you have something like that Super Mario game, in which the player can move either forward, can go up, or I think can also go down, can't go back. So there are 3 possible actions, and every time the player moves, that's a new state. So if you append that new state with the actions that are possible to that Q table, it's going to become extremely large. So the solution, the technique that's used, is this so-called experience replay buffer, which is a fancy term for a chunk of memory. It starts out blank, and you append a vector of values to that chunk of memory. You can have a million of them. Typically, a row is going to have 4 or 5 values. And so when you reach the bottom of that array, you just roll up to the beginning and recycle in that fashion. Now, the values that you put in each row with each vector are the values that identify where you're currently at, what state, what action, maybe the position you are, maybe a velocity, whatever indicators that are required to identify where you are in that game or that task. And so this is the interesting part here is 2 things. One, you can limit the size of this experience replay buffer. And the other thing is that it involves a concept called IID, which if you studied machine learning, if you've done deep learning, you know that one of the requirements, the constraints for your data is independent, identically distributed values. Well, when you have a player moving, there's a very strong correlation between a given position and a next position. So that kind of violates that rule, the IID for the data. So what you can do is to take a arbitrary subset of rows from the experience replay buffer, and that gives you the data that's IID. It's very clever. And so this is like when you're working with, again, with deep learning, you have stochastic gradient descent, and then you do your forward propagation, and then how many rows of data do you pass in? Well, you could pass in one row, you could pass in all, or you pass in a subset. It's called a batch, typically a power of 2. So you might select 16 rows of input, send it over to the loss function, and then at that point, periodically, it's going to do the backward error propagation. The same kind of idea with the experience replay buffer. There's also a priority experience replay buffer where you can assign priorities. Now, the third scenario is you have a dynamic number of states and a dynamic number of actions, such as a little robot car. So the robot car has a velocity, it has direction, it has, which is based on where you're turning the steering wheel. The steering wheel can go through from 0 to 360 degrees. All of those many, many values. Actually, it's an uncountably infinite number of possible values, but it's a huge number of values. So once again, we have the actions now expanding outward, just like we have with the states. So in this case, this is where we get deep reinforcement learning. Instead of using a Q table, we have a deep neural network where the input is the set of states which correspond to that dynamically randomly selected subset of rows from the experience replay buffer. So we have those states, and that the outermost, the final row, the output is going to be a set of actions. And what happens is that when you get to the rightmost hidden layer and you want to get to that output layer, you use the softmax function, which in turn generates creates a set of numbers. It's a discrete probability distribution. And so you look at the slot or the bucket that has the largest probability and go, aha, the action for the associated with that, that's the action that you take. It's very, very clever. And it's pretty much the way things are done with deep reinforcement learning algorithms. So the next thing I wanted to show you real quick, TD learning versus Monte Carlo. TD learning is temporal difference learning, which essentially means every time you take a move, you assess where you are, what you need to do. For example, if you are training a robot, you don't want the robot to fall over. So before that happens, if you can somehow detect that you're leaning too far in one direction, well, temporal difference learning is going to correct it and bring you back in the other direction. Or likewise with a bicycle. Instead of falling over to one side, you learn to compensate, and then you try to make sure you don't fall on the other side, and then you can ride your bicycle straight. So the choice of TD learning versus Monte Carlo depends on the severity of the outcome of failure. If it's severe enough, you use TD learning. If it's not, you can use Monte Carlo, which involves playing the whole game through, following the whole episode, creating a trajectory that from the start state to the end state, and then you assess. And I think that's what happens in a lot of card games, where people they've seen the whole pattern, and then they can make adjustments for the next game, which is, of course, would be like the next episode in reinforcement learning. And so just to give you a little bit more, the example that I showed you, our end-chain task, is known as a discrete finite automata. Given an action, you're in state, you're given an action, there's action 0 and action 1. There's only one path that you can take. There's only one other place that you can go to. Whereas, just to go make it a little bit more here, so we have action 0. If you're here, action 0 can only go here. Suppose now that instead of just having action 0 going from the left to the right state, suppose that we could also say we can go here. And oh, by the way, we can go here, and we can also go here. Now it's non-deterministic. In general, Reinforcement learning tasks are going to involve a non-deterministic scenario. And the next step from that, I'm bringing you up to the MDP. The next step is a Markov chain. And what does that do? It's an NFA plus probability distribution, which is to say, given any state, all the actions that emanate from that state have a set of probabilities whose sum is equal to 1. And then finally, MDP is a Markov chain with rewards. And that MDP is what's used to model practically any reinforcement learning task. So we're going to just have a few more slides. Something called Stochastic Actions, which is related to the NFA. And that means that this would be like our probability distribution. And we have a state, we have a set of actions, we have a set of probabilities, where of course the sum equals 1, they're all non-negative. So as an example, and this actually is the case for the grid world, which you can find online. The deterministic scenario says that if you say that you're going to go forward, you're doing so with probability 1. And that's okay, that's fine. But the more interesting scenario is when it's stochastic. And typically, this is just in general what you'll find, the scenario is you say you're going forward, but it's only 80% of the time that's true. And 10% you're going to go left, 10% you're going to go right. So that gives you a lot more scenarios, a lot more randomness. So that's where you can think of the Epsilon-Greedy scenario, the exploit versus explore. That gives you the ability to explore many more different trajectories. So that's what you can typically see with a lot of algorithms. They're going to involve stochastic actions. Here's an example. I'm going to give just very briefly. And this is actually purely random. We install OpenAI Gym, it's open source, and import it. And then we create an environment. And the environment is for this so-called CartPole. There's a lot of other tasks that they provide you. The CartPole is like a little rectangle, and then there's a stick above it. It's much longer, and you're trying to move the thing back and forth to make sure that the pole stays pretty much upright, or at least it doesn't fall over. And so how do we do that? This one won't, but it gives you the core code that you would use. So we have a set of episodes. I chose 20. And each time we enter this loop, we do a reset because it's going to actually draws a little picture. You run it in a command shell, and it'll show you the state of the cart and then the pole, whether it's wherever it's situated. And so what we do here in this inner loop is we iterate 300 times where we display the environment, that image, and then we take a step, which you notice here is ENV action space sample. That means find a random action, pure random. And so what's going to happen if you actually run the code with the necessary pieces in there, it's just going to have that little piece, the cart is just going back and forth, and it's just flopping around all over the place. Pretty much useless in terms of actually accomplishing the goal. But now in this one, we're doing a little bit better here. What we've added is the action now is based on Epsilon-Greedy select action, which is a function that's not listed here, but implements Epsilon-Greedy. And then we look at the result of taking that action. We take a step, and this method returns 4 values. The next state, the reward, the done flag, and then info is just a Python dictionary with some metadata. Typically, you don't really look at this much. And so the reward that's where we're getting. We took an action based on a current state, and it's going to tell us what our next action, like we went from S00 to S state S3, and the reward, and then whether or not it's done. Now we have to set the state variable equal to that state that was returned, so it's going to repeat. And then if it's done, it's going to break out of this loop. So that's a little bit better. At least we're using Epsilon-Greedy. Now in this one, we're adding a little bit more specified with new here in the comment. Now we have an array here, or list rather, a trajectory. And whenever we fall through here, notice we append these values here. This would be like the values that you would put in an experience replay buffer. But we're just putting it in this list here. And then later on, if you want, you could print the values out, compare them, see which one is the maximum reward, and so on and so forth. Keep in mind, though, that the reward hasn't been discounted. And that's what this one does. We're looking at a new list, which involves the cumulative rewards. We have our discount factor, time step, and now this is the G0 is what we're going to use for the expected future return. And it's the one new step is right here. This return is going to be incremented by, remember we had gamma to the first power, gamma squared, cubed, and so forth, times the time step, and then times the reward. This is the R1 through Rn. So it's G to the power time step times that, and we increment our time step. And then we add that, when this loop is finished, now we add that new future return to this array. So now we can dump out those values, we can compare and see which one has the maximum. I know, I apologize for going so quickly through this, but it just kind of for the sake of time, I just want to make sure I get through this. And so more things that you're going to end up seeing if you end up reading more about reinforcement learning. The environment, that's the ENV that I was talking about that you saw with the OpenAI Gym. The discounted reward we talked about. The agent is the thing that's moving around, like the CartPole itself, or Super Mario, or whatever the thing is going through the maze. These other things I won't talk about, but you can find out about them. Policies, another important aspect of reinforcement learning. Here's a ton of algorithms, and you, in addition to this policy, kind of policy, off policy and on policy, model-based, model-free. Q-learning happens to be model-free and off policy. These are this list of algorithms contains the deep reinforcement learning algorithms, generally the ones with a D. And so these two in particular handle continuous states and actions, kind of like that third scenario that I was talking about before. This here, I mentioned this here because there's robot cars from AWS actually use this PPO, which is proximal policy optimization, which is a simplified version of this trust region policy optimization. I know this doesn't mean much right now, but later on it probably will. And this happens to use KL divergence. So it gets a little bit kind of gnarly in terms of the details. It's not quite as clear as a simplified PPO, which is actually almost as good. And so here are some of the libraries that you can explore. And the one from Google, it is actually called Zopamine. I always thought that was funny. And TF agents, Keras is another one, Keras-based reinforcement learning. And OpenAI Gym, these are some of the tasks. We talked briefly about this one. Here are some other ones. They're all toy tasks, but they give you an opportunity to implement reinforcement learning algorithms. And this Mujoko is this other alternative. It's a third-day trial, I believe. And so if you want to get very deeply involved with reinforcement learning, you can find lots of detailed art papers in archive, and there's some very decent articles that are available on Medium. And some of the people here, Peter Abil is very heavily into robotics. He's actually the co-author of the PPO algorithm. David Silver is in charge of, he's the lead for the team that plays those online games like Dota 2, and I don't play those online, multiplayer games, and they've done it remarkably well with their algorithms. And Andre Karpathy used to be at Tesla, it's moved on. And so this is the final slide with the links, and this is the one that has that formula that I showed you, calculating QS for a state in action. And this is very interesting. This multi-agent reinforcement learning, they actually used simulated ants. Now, why in the world would they do that? It turns out there's something very interesting about ants. You've probably seen them, when they're going to pick up some food, they're single file, very, very structured and logical. But you may have seen sometimes how they are in the anthill. They're going, some are going in, some are going out. It's like a kind of a frenzy, and it looks like a madhouse. Well, here's the thing about those ants. They never collide with each other. Isn't that interesting? How in the world do they do that? Nobody knows. And so that is some people are using to try to emulate that activity in order to implement multi-agent reinforcement learning. And this is an article, gives you more details. Richard Sutton is one of the premier reinforcement learning scientists. There's a 700+ page book that he co-authored, free PDFs available, including their website. I think they have it as well. And that is very, very intense, intense book. Sort of, they call it the Bible. And finally, totally shameless plug for UCSC, where I'm here as an AI instructor, and you can find a list of courses there. So we finished with about at most 60 seconds to spare. We don't really have much time for questions, but I think if perhaps in the virtual book signing, we could do that as well. Okay, I hope this was worth your time. Thank you for your patience and attendance.